Hello and thank you for your time. I would like to introduce to you IoT Ranging. IoT Ranging has developed an operating framework for synchronized communication between IoT devices and the IoT network, and two, developed a process to determine accurate time of day and distances between IoT devices. Together, these innovations eliminate signal traffic and interference and ensure data accuracy and reliability. They improve navigation and protect the safety of moving objects in any environment, and set the stage for advancements in smart infrastructure and the future of navigation management. Our intellectual property is protected by 27 utility patents, 2 of which are pending and 1 will be filed early next year. We have a detailed list of each patent at the end of the presentation. Currently, only moving objects have ranging capabilities, and not all moving objects have these capabilities. Those that do work in isolation without any sort of organized signal ranging and communication. These individual isolated systems cause many problems, including signal traffic, signal interference, data inaccuracy, and unreliability. Furthermore, when a network is unavailable, there is no secure protocol in place to allow for uninterrupted communication between objects. This compromises safety and leads to inefficient and even blind navigation, and ultimately leads to poor navigation management. There is a need for a synchronized system-level solution. IoT Ranging has developed a system solution for ranging and communication between IoT devices and the IoT network. This system is based on a frame model which has a start time, a set duration of operating time in milliseconds, has multiple time slots in microseconds, and repeats indefinitely. The IoT network assigns each IoT device a specific time slot to range, transmit, and receive signals. This protocol streamlines organized, synchronized, and uninterrupted transmission of operation information and data between objects. The following are terms definitions for your reference. Every object in any environment is represented by an IoT. Further, all operating space, whether land or air, is divided into smaller sections called cells, for which the IoT network has terrain maps. Every cell network uses the same frame duration and has its own IoTs with time slots, frequency, and channel. Of course, dynamic movement causes time slots to fill up and free up as objects enter and exit an area. If there are too many objects for the number of slots available in a cell, then the IoT network will split the cell area into smaller cells that may use a different frequency and channel to accommodate the increase. Within each cell, there are moving, flying, and stationary objects, and all objects have a master IoT or slave IoT. Some have both, and they communicate through a controller. Furthermore, all data is transmitted to the cloud through the IoT network. Let's use automobiles to review the steps involved in data exchange between objects. When each automobile powers on, its master IoT is registered with the IoT network, which sends its ID and specification to the cloud's operation management center, and then to the cloud database to be saved, shared, and regularly updated. Once registered, each automobile receives the time of day, operating information like frame duration, absolute start time of its time slot duration, and any relevant environmental data like terrain maps and road conditions from the cloud through the IoT network. Time of day can also be received from GPS satellites. The master IoT communicates time of day and operating information to the controller, which then informs the slave of their exact time slot and operating frequency and channel for ranging. In this example, real operating time has been slowed down from microseconds to seconds so that signal transmission is easily visible. As the automobiles pass each other, their IoTs range and communicate only during their specific time slot. Their master IoTs update time of day, send location coordinates and other relevant situational information like accidents or malfunctions to the cloud through the IoT network. The cloud's Operation Management Center has access to all data, stored in the databases or updated from the network. It monitors everything communicated and transmits operation information to objects through the IoT network to improve overall navigation and safety. Let's now look at how master and slave IoTs exchange data. In the first example, a moving object is exchanging data between its slave and master IoTs with the network. In the second example, slave IoTs on stationary objects like road dividers and reflectors are communicating with the road's master IoT, which is transmitting information to the network. And finally, you see each stationary object communicating during its own respective time slot, not simultaneously. The future of smart infrastructure will require all objects to have IoT devices and for those devices to have accurate time of day. Why is time of day important? Well, because all IoT devices must know the operating frame duration, their time slot's absolute start time, and that time slot's duration to know when and how long they can range and communicate. Furthermore, our framework calculates distances between objects by using time. The next animation shows IoT devices ranging to calculate distance. Now, the critical calculation here is delay, or the time it takes for a signal transmission and reception to occur from timestamp to timestamp. Signals are sent back and forth twice, at which point both IoTs have 4 separate timestamps that they can use to calculate delay. Once delay is determined, they have accurate distance, since data is sent at electromagnetic speed, 1 foot per nanosecond. And if for any reason an IoT device cannot obtain its location coordinates, it can determine this through triangulation with stationary objects, because location coordinates of stationary objects, they don't change. It should be clear now that accurate time of day is essential to directing all objects in all environments. And we're talking about accuracy in tenths of nanoseconds. GPS satellites have accurate time of day, UTC, which they share with the IoT network and with IoT devices that have oven-controlled or atomic clocks. But most devices don't have these types of expensive clocks. The master IoTs of objects like buildings, road infrastructure, and some automobiles do have them because the price of the clock is negligible compared to the price of the object. If network is lost, they can get accurate time of day directly from the GPS satellite. And if the satellite connection is lost, their atomic clocks have a holdover period where they maintain accurate time of day for up to a few hours or a few days until connection is reestablished. But what about all the other master IoT devices without these expensive clocks? Those that can't get accurate time of day from the GPS satellite or hold over and maintain themselves without time drift. They get accurate time of day from the IoT network since it's cheaper and can regularly update. But then what happens when the network connection is lost? How do those IoT devices determine their accurate time of day? In these cases, the IoT without time of day can seek out accurate time from any nearby object with an atomic or oven-controlled clock. After sending a broadcast request for time of day, another object with the right clock will pick up the broadcast and go through, again, a 2-step signal sending process to calculate the time offset between the two. Once offset is determined, the first object can correct its time. Now, if an IoT device loses network connection, remember, it doesn't lose frame duration or its time slot, only accurate time of day. And in the future, low-cost accurate clocks with holdover of 1 to 2 hours will be available. And then if the IoT loses network connection, it can still operate within those 1 to 2 hours with a low-cost oscillator until network connection returns. Now, in the next few demo videos, time has been slowed down from microseconds to seconds. Real operating time, of course, is 1,000 times faster with thousands more signals being sent. Furthermore, you will notice that in all of these videos, all IoT devices communicate and range only during their respective time slot, never interrupting signal transmission of another IoT. Here is a typical two-way street. There are IoTs on stationary objects like buildings, lampposts, trees, and lane and road dividers, as well as on moving objects like automobiles. Road infrastructure IoTs are lane and direction specific. They do not transmit into opposing or oncoming traffic. In addition to IoT ranging, moving objects can use radar, LiDAR, ultrasonic sensors, and image sensors for ranging. In the future, robots may also roam alongside people as moving objects with IoTs. Next is a moving object entering a main street. While only ranging and communicating during its time slot, the automobile's IoTs have gathered data about other objects and about street conditions. Its controller's artificial algorithm determines when to brake to avoid collision and when it's safe to continue. The controller has also received information from stationary IoTs about an empty parking spot. After turning right, the automobile promptly parks. Here is a typical four-way city intersection. During their respective time slots, the traffic lights' IoT devices send their current status. If currently green, they inform other IoTs of how many seconds until the light will turn yellow and then red. Next, we have an automobile or automobiles changing lanes on a freeway. You'll notice the typical buildings, trees, and traffic lights aren't visible. They're farther away. Instead, the automobile gets data from stationary IoTs that are located on the freeway infrastructure, like the freeway divider, the lane dividers, side railings, lampposts, and the IoT network base station towers. Here, the stationary objects also provide the speed limit and distance to freeway exits. Next is a crowded freeway with much more activity. Here there are also IoT devices on the freeway on-ramp. The entering automobile gathers data from all moving and stationary IoTs about other moving objects and the freeway conditions. Its controller's artificial intelligence algorithm determines at which speed to enter in order to keep a safe distance from other vehicles. On the opposite side of the freeway, an automobile detects a problem. Its controller uses data to determine when and where to safely pull over to the shoulder. And the last example applies to moving objects on country roads, mountainous roads, or traveling through a tunnel. Often in these conditions, IoTs cannot connect with the IoT network or satellite because the signal is very weak. Network reflectors and repeaters are positioned at the top of mountains, allowing for all IoTs to access the network and satellite data to overcome the weak signal issue. Here, road and environment infrastructure is also critical. In addition to the IoT devices located on the road railings, road dividers, and lane dividers, there are IoTs throughout the tunnel. They all have special sensors that can sense weather and temperature to determine road conditions, and they broadcast object data along with height clearance, road curvature, speed limit, and road maintenance information. The future of effective navigation management will require all objects to 1. Have IoT devices, 2. Have accurate location coordinates, time of day, operating frame, operating time slot, and 3, the ability to determine their distances and time of day even when satellite or network connection is lost. IoT Ranging has developed a system-level solution that streamlines organized, synchronized, and uninterrupted transmission of data between objects, setting the stage for advancements in smart infrastructure and the future of navigation management. Thank you for your time, and please reach out to our team with any questions that you may have.